Hey, this is a quick screencast on the idea of rates of change. It's going to lead us into the study of derivatives, and I thought I would just give you a quick overview and give you a way of thinking about what we're going to be studying next. Let me start with what we're studying now. We're studying continuity, and a function is continuous at input c if this limit statement is true. And this tells us something important about a function, but it doesn't tell us, it's kind of generic. So what it tells us is, it tells us that if I've got a function that has this limit property, the graph kind of looks like this. The function goes through the point c comma f of c, and the graph comes in on the left and goes out on the right. Now, it could also look like this. It could come in from below on the left and go out above on the right, or it could come in directly from the left and go out directly on the right. These are the three qualitative things that can happen. This limit statement tells you one of these things is happening, but it doesn't distinguish between these three things. What we're going to do now is look at this idea of rates of change, and it's going to help us distinguish between these things. Now, rates of change these are concerned with the idea of what happens to the value of y if we change the input. Okay? So in this context that we're working in right here, in the context of this limit statement, we're going to start at the point c comma f of c. Okay. And we're going to change this by a little bit. And then we're going to ask, how much does this change? Right? I'm going to call that change delta y. So let me draw a picture of what's going on here. So suppose we have a situation where our function looks like this, and I'm going to add a delta x onto my input. So in the picture, this distance is delta x. Well, adding that delta x pushes my point up the graph that direction, and it ends here. And so that's got a y value that's up there. So this value up here is f of c plus delta y. So this distance that the y values have changed is what we call delta y. So this value, this delta x, this change in the input, leads to this change in the output. And what we're going to look at is this ratio delta y over delta x. It's going to be like a factor. It's going to be like a conversion factor. And the delta y over delta x is going to tell us if I increase the input by so much, the output is going to increase by that factor. So if input changes by delta x, then output is, so this ratio is the multiplier, and we can get our new delta y from that. And you can just look at this and you can see, yeah, those delta x cancels and you're left with a delta y. But this ratio delta y over delta x, it's going to be we're going to think of that as a constant, a multiplier. I also want to say that our delta x and it could be negative. And if my delta x was negative, and I added it to my input, that would give me a point to the left of C, my starting point, and I put the resulting ordered pair there in orange, and you can see we get a resulting output. And so there would be my f of c plus delta y, and here's my delta y for that case. So it's helpful for us to be more specific about what these deltas are. So I'm going to do that right now. So first thing you should know, delta is the uppercase Greek letter. Okay, and we use it when we want to talk about change. So the way we're going to define our delta x is we're going to look at it as a difference between our two values. So the difference between our new or our resulting input, in this case for delta x, and the old input. So in the case of this picture that I have over here, our old input is going to be 1, will always be 1, and we'll always be changing that. Our deltas are going to be relative to that 1. Likewise, delta y is going to be our new y value minus our old y value. And in these cases, y is always going to be 1 as well, because that's what f of 1 is. It's important to notice that these definitions endow the delta x and delta y with a sense of direction. Okay? If the delta is greater than 0, then the quantity is increasing. If the delta is less than 0, the quantity is decreasing. So look at delta x, for example. If my new x value is bigger than my old x value, then this difference is going to be positive, because you're taking a big number and subtracting a smaller number from it. If my new value is smaller than my old value, then I'm taking a small number and subtracting from it a bigger number, and I get a negative number. Okay? So another way to think about up and down is in terms of being on a number line. So when you go up, we're moving right along the number line. When you're going down, we're moving left along the number line. So a delta that's positive means we're going right up the line. A delta that's negative means we're going left or down the line. Okay, so let's do an example of how this works. We're going to do an example where we're going to calculate a bunch of delta y, delta x's for a function that we understand. And then we'll call it the end to the screencast. So the function I want us to study is the squaring function. And we're going to take c equals 1 be the place that we're working from. And so that means, now we don't have necessarily always know what the graph looks like, but we do know that the squaring function kind of looks like this. It goes to the point 1, 1. So everything we do is going to be based off of being at 1, 1. So these are our starting or our old inputs. And then we're going to try to figure out what our new inputs are. So I'm going to, let's start with an easy delta x. We're going to say, what happens when delta x equals 1? So if I add 1 to my input, my new input is going to be delta x plus c, or 1 plus 1. And then my new output is going to be f of 1 plus 1. That's f of 2. And so I square 2, I get 4. Okay. So that tells me my delta y, okay, it's my new y value minus my old y value. So delta y is 3. So in this case, we've just calculated delta y over delta x is 3 over 1, which is 3. So the way we interpret this is, when we start out at 1, it's like my function is multiplying the outputs, the size of the outputs. Or it's to get the size of the outputs, you're multiplying the input size by 3. So the function is trying to magnify the the size of the input. We'll see that this is just an estimate because we kind of just picked that number at random, the delta x equals 1 at random. So this is just an estimate of what that multiplying is doing. We'll be able to get a better estimate of it as we go along. So let's look in the other direction. What if we decrease our input? So our delta x equals -1. Then c plus delta x is 1 minus 1, which is 0. And then the value of my function at 0, well, you square 0 and you get 0. So our delta y, it's the new y value minus the old y value. So our delta y is -1. And so if I go and compute delta y over delta x, I get -1 over 1, and so I get 1. So now it looks like the function, if I move to the left, my function isn't magnifying the change as much. It's keeping the change the same. My multiplier is 1. So I go to the right, it's 3. I go to the left, it's 1. Okay, that's weird. So let's notice something here. Let's make my delta x smaller. So if x is a half, then c plus delta x is 1 plus a half. That's 3 halves. Then my function at 3 halves, you square it, so I get 9/4. So what's my delta y? Well, it's 9/4 minus 1, right? My new y value minus my old y value. And that's 9/4 minus 4/4, so that's 5/4. So delta y over delta x, it's 5/4 over a half. So dividing is the same thing as inverting and multiplying. And so we see here I get 5 halves, okay, or 2.5. If you do the same thing for delta x equals -1/2, you're going to get delta y. See, I calculated this, is 3 halves. Okay, 1.5. So if you notice something that happened here, the numbers changed when I made delta x smaller. So going to the right, it was 3, now it's 2.5. Going to the left, it was 1, and now it's 1.5. Now if I make a table of values, so this table magically appeared. Notice what's happening. As I make my delta x's, keep them positive but make them smaller, the delta y over delta x's are also getting smaller. And look at the same thing for the delta x's that are negative. As I make them smaller in size, the delta y over delta x's are also getting smaller in size. If you made delta x smaller and smaller, you'd see that the limit as delta x goes to 0 from above, so these are all positive, of delta y over delta x, those are getting closer to 2. And as the limit as delta x goes to 0 from below, so they're all negative, of delta y over delta x, those are also equal to 2. So these two one-sided limits agree, and so we can say the two-sided limit exists and equals 2. So this is kind of cool, and it means that maybe this number has an important interpretation or an important meaning for the function. This number does have an interpretation, and it's this. And so here's the graph. This number, the squaring function's nice and smooth. It's continuous, and it's even nice and it's nice and smooth. We can draw this thing called a tangent line, and this tangent line turns out it has slope equal to 2. And this slope is called the instantaneous rate of change. Of the squaring function at x equals 1, so at that point. Okay. And this is the idea of derivative. So we're going to be interested in these trends, this way that the function stretches and magnifies changes in the input into changes in the output. And we're going to measure those through a process that's called differentiation. So this should get you going. Check my numbers, maybe work a couple more examples, like work maybe the same function, the squaring function, but for an input of x equals 2, and see what you get in the limits. And we'll talk more about this in class.